Hey guys, so here's second semester. The main concept we've looked at so far is antiderivatives. But before we go into antiderivatives, let me just take some time to make sure that you guys are really good with derivatives. And then once we're good with derivatives, we can go to antiderivatives. So maybe you can jot this down somewhere. Now, I don't know how long this video is going to be, but you should know that this video is meant to be a summary, not for 1 or 2 days, but for like a whole week. So just understand it, right? We're going to recap a whole week right here, right now. So on some paper, maybe you can just jot down derivatives. Let's just go over the facts of derivatives. We'll do a few derivative examples, and then we'll discuss antiderivatives. And so that's the agenda for this video, okay? So let's see. So remember that if you have some function f of x, let's make like a chart, f of x, and then over here we can go like f prime of x. Let's just make like a little chart. Okay, we'll switch colors now. So let's suppose that you have some function that says like x to the n. Then the derivative f prime would be n times x to the n minus 1, right? Now, what about if you have some function, let's say e to the x? What is the derivative, right? If your f is e to the x, then f prime, the derivative would be, I'm gonna write it like this. I'm going to write down e to the x times dx. And I'll explain what dx is in just a moment. For now, just bear with me here. So what if I have some function ln of x? Then the derivative of that would be 1 over x times dx. What if I have some function a to the power of x? Then its derivative would be a to the x ln a times dx, right? And what if you have something like log base a of x? Well, its derivative would be 1 over x ln a, and then off to the side, times dx. And as a matter of fact, before we go any further, if I go back to the very first one that I wrote down, x to the n, the derivative would be n times x to the n minus 1. Really, let me just put times dx. Just for the sake of consistency, I'll also attach a times dx, okay? And so far we have these here. There are more facts and rules, like for example, how about like sine of x, right? Sine of x. Well, the derivative of sine would be cosine x times dx. What about the derivative of cosine? The derivative of cosine was negative sine x times dx. And I'll just write the words like etc. because there were more functions that we discussed, like more trig functions. But you have those on your notes. But the point of this is just to recap derivatives. Now, let me explain what this dx is. So let me just jot it up here. I'll say where dx represents the derivative of x, right? Whatever is playing the role of x, that object x, whatever it is, then dx is the derivative of that object. Now, we will do a bunch of examples right now, to make sense of this. And then once we've done a few examples of derivatives, then we can discuss antiderivatives and call it a day there. So let me just separate this into 2 parts. Let's do some examples here in purple. So let's do a bunch of examples where the goal is to find f prime. Okay. So example A. So hopefully you're jotting this down. And let's see. So for example A, what if I have something like, let's say 5x to the power of 4? Okay. Let me just call this f of x. Let's just be proper here. Let's call this f of x. F of x equals 5x to the power of 4. Okay. Well, the derivative, if you guys use the power rule, remember the power rule where you go 4 times 5, and that'd be 20x, and then you take away 1 from the 4 to get a 3. And that's what this says here, right? X to the n, its derivative would be n, and then x to the n minus 1. Now, times dx means that you have to multiply right here. I have to multiply by the derivative of whatever is playing the role of x. Well, in this problem, playing the role of x here is literally just x. And the derivative of x is just 1. So I'm going to just multiply by 1. So that's not going to change anything. It's just going to be 20x to the power of 3. So this example here, although it's an easy example, it doesn't really make clear what I'm telling you about this object dx. So let's do an example where this becomes crystal clear right now. Example B. Let's say you had a function. Let's say it was like e to the power of, let's say, how about like 7x to the power of 2, okay? So I think with this example here, these rules here are going to become more clear. So let's see. So here's my derivative. Maybe I can switch colors for the derivative. So let's call this f prime. Well, look at your facts. How the heck do you find the derivative of e to the whatever? Right here. E to the whatever becomes, first of all, itself. So let's just copy and paste the original function. E to the 7x squared times, and then it says times dx, where dx is the derivative of whatever this exponent is. Well, for my example, the exponent says 7x to the power of 2. So I want your eyes to look only at the stuff there in yellow. Please tell me out loud the derivative of the stuff in yellow. The derivative of that gibberish in yellow is 14x. And so I'm going to put 14x right there. You see that? This here, this 14x, that's playing the role of dx, where dx is the derivative, right? It's the derivative of whatever was playing the role of x. In this case, playing the role of x was 7x squared. Okay? Let's do another one. Back in purple. What if I have something like this here? Let's go some function, and let's say that it equals, how about like the sine, parentheses, of, let's say 8x, close parentheses. And we want to find the derivative, okay? So we have f prime equals, well, how do I find the derivative of sine? According to my rules, the derivative of sine is cosine, right? The derivative of sine of blah, blah, blah is cosine of the same blah, blah, blah. And so this would be sine of 8x. But then I have to multiply by dx. JK, the derivative of sine, of course, is cosine. Silly little Lee. But then I have to multiply by the derivative of x, right? That's the whole point of this little piece that says dx. It's the derivative of whatever this guy was. Well, for this problem, the derivative of 8x is just 8. And so I'm going to put an 8 right there. And that would be it. That's how you find derivatives, right? But before we go to antiderivatives, let's just do 2 more. Let's just do 2 more quick derivatives, and then we can move on. So let me just erase this here. In the meantime, you can just, relax your wrists or get a drink of water or something. Let me just erase some of this stuff here. So that was examples A, B, and C. Let's do D and E, and then we can do antiderivatives. So let me just make this up here. Let's suppose that, for example, D, let's go with a red marker this time. Here we go. Example D. Let's say our function f of x. Let's say it's like, how about like 8 times 3 to the power of, let's say, 4x cubed. Let's kind of hard to see, but it's right there. Okay, so let's see. So we want to find the derivative of this object. So let's go f prime of x. Now you got to recognize what kind of function this is. So look at your cheat sheets, right? This here looks like which one of all of these options? Well, I think that it looks exactly like this one here. It's a number and then to a certain exponent. I know that there's an 8 that's sort of just like bothering us. So just copy and paste the 8. The 8 just falls down. Now let's find the derivative of this object here. And this, of course, looks just like a to the x. So the derivative of a to the x is, first of all, itself as is. So that'd be 3 to the 4x cubed times. And then it says times natural log of whatever is playing the role of a. Here, playing the role of a is 3. So this would be ln of 3 times. And then you have to multiply by dx, where dx is the derivative of whatever this object is right there, where the cursor is pointing. Well, for our problem, what was playing the role of x? Here, 4x cubed, right? Or this guy up here if you want, 4x cubed. So what's the derivative of 4x cubed? 12x squared. So right here, we'd go 12x squared. And that would be it. That's our derivative. Right, so really, so far, we've just revisited the chain rule, as it's called. I should have just told you at the start, we're looking at the chain rule, because that's what this is. It's the chain rule made simplified, or made simpler. One more, guys. What if we have, like, let's go with log base 7, parentheses, let's go e to the power of 13x. Let's make this a little more interesting. And we want to find this derivative. So how do I find the derivative of log? Well, let's see, it's right here. The derivative of log base a of x is going to be 1 over some stuff. So let's see, so this derivative is going to be 1 over some stuff. But what goes in the bottom? It's 1 over. What goes in the bottom here is whatever is this one. So here for us, it's going to be e to the 13x. And then what else is in the denominator? It goes times the natural log of a. So times the natural log, in this case, 7, right? ln of a is whatever the base is of the log. And then we have to multiply by dx. So times, and dx is the derivative of whatever this object is. Well, for us, that object is e to the 13x. And so what's the derivative of e to the 13x? Well, that's when you have to use this rule, right? So that would give us e to the 13x times, can you say it out loud? Times 13, right? Because you have to multiply by the derivative of whatever this is. So this one here, and that was kind of sneaky, right? Because it's like a chain rule, but it had like a lot of layers that we have to peel off. So anyways, guys, hopefully that helped in terms of a refresher for derivatives, specifically the chain rule. So now, why don't we look at this idea of an antiderivative? And that's what we've been looking at so far in the first week, antiderivatives. So let's look at that right now. So now we're going to play this game, but completely backwards. I'm going to give you a derivative, and you're going to tell me the original equation. That's the derivative. Okay, so it's called the antiderivative. So pencils up. Let's do a bunch of examples, and then maybe we can give you like some cheat sheets and stuff, or some shortcuts. Yeah. So let's say that you don't know the original function, but what you do know is the derivative. Let me just make this up. Let me just call this 3x squared. So again, we're just brainstorming for now before we do any examples. So can you tell me an equation that the derivative of that is 3x to the power of 2? Well, I mean, I asked this to my students and they were like, oh, I think I know the answer. And they said x cubed, Lee. And I was like, hold on. You think that x to the power of 3 is the antiderivative of 3x squared? And they said, yes. And I said, all right, let me check this. Let me just take the derivative. Let's just pretend that you have x to the power of 3. What is the derivative of x to the power of 3? Well, you use the power rule. You know there's a 1 right there. 3 times 1 is 3x. And then you take 1 away from 3 to get 2. And these perfectly are equal, right? So yeah, you're correct. This is what we call the antiderivative. But there's more to it, because look, what if I did this? What if in pink, what if I said like plus 11? Would this be acceptable? Would this be a good antiderivative for this? Yes, because if I take the derivative of this, the derivative of x cubed is 3x squared, and the derivative of 11 is 0. And so that's appropriate because there's technically like a plus 0 right here, right? So this would actually be fine. But what if instead of 11, I put like 110 or 1,105 or whatever number this is, right? See, all of these are acceptable because this is a constant and its derivative would vanish. So as a general rule of thumb, this is what we do when we do antiderivatives. We don't put a specific number per se. We just put plus c. And you should know that this is any real constant. Let's just pretend that it's real. Any real constant. So whenever you guys are finding antiderivatives, you do like the thing, and then you put plus c. Because, you know, there could have been some number there, who knows? Before we do some antiderivatives, what if I give you guys a cheat sheet right here, right now? So you really want to copy this down. So let's do like an antiderivative derivative cheat sheet. So let's do this in blue here. So if you have someone that the derivative looks like x to the power of n, then as a result, the antiderivative would say this here. Or the antiderivative would be this here. 1 over n plus 1 times x to the n plus 1. If you have someone that the derivative of it is something like e to the x dx, if that's your derivative, then your antiderivative would, of course, would have been e to the x. If you have someone that the derivative looks like 1 over x dx, then the antiderivative is ln of x. What if you have something like 1 over x ln a dx? Then its antiderivative would be log base ax. What if you have something that looks like a to the x ln a dx? Then its anti would be a to the x. And there's more, and let me actually copy those down here. Let me use the other side of this paper, of this board. Antiderivative, space, 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 derivative. Why don't I jot down for us the trig ones, right? All the trigonometric ones. So what if you have a derivative that it looks like, let's say, cosine x dx? Then its antiderivative would have just been sine x. What if a derivative looks like negative sine x dx? Then it came from cosine x. What if you have secant squared? It came from tangent. Let's see, what else? I think there's 3 more that I want to give you guys. Okay, this one here. Oops, let me bring back my whiteboard. I think I just lost it. Let me just type this a little bit smaller. Negative cosecant, cotangent. That would have come from cosecant. And then secant has secant tangent. I think there's one more. This guy here. Okay, so jot those down, guys. And I think that these are all that I wanted to give you. Let's take a gander here. Let's see. Yeah, this looks pretty good. So guys, here's the point of this cheat sheet. I'm about to give you guys a bunch of derivatives. Your job is to give me the antiderivatives. So if your derivative looks like one of these guys here, then the antiderivative might look like something to the left, right? That's the point of this chart. Now, I do have to get rid of this so I can actually write down some stuff. So I need you to really copy these down and have these with you nearby, because all these are going to have to go. So what if maybe I can just give you guys like example. Let me erase just this right hand side. So let's do a bunch of examples here. And maybe first I can do examples with the things that I'm going to leave here on the left. So for instance, here we go. Let's do some antiderivatives. Let's go like that here. So it's going to say example, find f of x, right? You want to find f, the original function, because I'm going to give you the derivative. You have to give me the antiderivative. So here we go. Let's see, we have x to the power of 24. So here I have a derivative, x to the power of 24. And I want the antiderivative. So what I do is, because this is a derivative, I look at the derivative column and I ask myself, okay, this one looks like which of these? Well, it looks just like the first one, the x to the power of a number. And so the antiderivative is given by this definition here, 1 over n plus 1 times x to the n plus 1. And so here, this would be, this f of x, the original function, would be 1 over 24 plus 1 times x to the 24 plus 1, which of course is simply 1 over 25 x to the power of 25. And of course, plus c. You should put a plus c. Right? You should put a plus c, just in case, because it could have been some number there. And that's it, right? So this is your antiderivative. And you know this is correct because you can check it. If you take the derivative of this in your head, you should get back the original question. Watch. Find the derivative of this in your head. 25 times 1/25 is 1. It goes away. And then you take 1 away from 25 and you get back 24, which is this, what this says. And then the derivative of any real number would be 0. And there's a 0 right here. So that's how you know that this is correct. Okay. What about example B here? And let's make this a little more interesting. So what if you have something that says something like this? Let's go with f prime of x equals, let's say, how about 8e to the 8x? Well, look, what I was doing with the class the other day, I was sort of kind of doing like a guess and check method, like a guess and check technique, where here, what I can do is I can guess the original function, and the derivative of my guess is supposed to be this up here. So someone can say, oh, well, I think my guess for the antiderivative would be e to the 8x. And let me just check this. Let me find the derivative of my guess. So if my guess is e to the 8x, what's the derivative of e to the 8x? We'll do what you did in the first part of this video when we found derivatives. Well, the derivative of e to the 8x is, first of all, itself times dx, which is the derivative of the exponent. And the derivative of 8x is 8, which you can put right here if you want to. And look, that matches perfectly with what we want our derivative to be, right? I wanted a derivative that says this, and that's exactly what this is. And that tells me that my guess was on point. And so we have found the derivative or the antiderivative on the first guess. So it's e to the 8x plus c. So whenever you're doing this, like on a homework or quiz or classwork, whatever, you can check your antiderivative for accuracy by taking the derivative of it. So if I take the derivative of this, do I get this back? Yes, I do. And so this is correct. Okay? Let's do several more of these. What if you have a function, and let's say that it says this here. Let's suppose that it says, what if it just says something like e to the 5x? And here is where we're really going to learn something here. Let's continue with this guess and check technique. Here is just my guesswork. I'm going to guess the antiderivative. I'm going to find the derivative. And if I have to, I'm going to modify it until it matches what it's supposed to be. So watch. So if anything, why don't you just go pencils down and just watch this right quick. Let's suppose that you think that the antiderivative is this. This is your guess. Let me find the derivative of my guess. The derivative of e to the 5x is e to the 5x times 5. Now, this is no good. This is not correct because my derivative is supposed to be this. And I like some of this, but not all of it. You see that 5? If that 5 was gone, we'd be good because it's supposed to look like this. So how the heck can you get rid of this 5? What you can do is you can multiply by 1/5. But however you modify this, you have to modify this as well. So if I multiply this by 1/5, I here and multiply this by 1/5 as well. And what the heck was the point of multiplying by 1/5? The point of that is that this 1/5 knocks out this 5. And I wanted this 5 to be gone so that it just says e to the 5x. And I wanted to say this because that's exactly what this says. You see that? And so now that I have found the correct derivative, this reveals to you the antiderivative. And so we're done. So this would be 1/5 e to the 5x. Just put a plus c if you want to. So this is the philosophy that we've been employing in this class, where to find an antiderivative, bro, you just make an educated guess initially. And then whatever your guess is, you find its derivative. And then if you have to, you modify that derivative until it matches what it's supposed to look like. But of course, whatever modifications you make to this, you have to make to this. And once this looks like that, then whatever this is, ta-da, that's your answer. Okay, so let's do maybe 2 more examples, and then we can call it a day. So what if you have a function that looks like this here? Let's say you have an equation or a derivative that looks like, let's say, 20 to the power of x. Okay, that's your derivative. So it's like, wow, I mean, how do I know? Where do I start? Well, this is a derivative. And what I recommend that you do is you look at your derivative column and ask yourself, this guy, which one does it look like? Does it look like this one, this one, this one, this one, this one? You might think that it looks like the first one, but no. This does not look like this. Because here, this is a variable and this is like a number. This is backwards. This is a number and this is a variable. So what I think that this one looks like this guy because there is a number and a variable. And I know there's some baggage attached to it, but it's okay. I think that this one looks like this one. So let me make a guess. Because this derivative looks like that, I'm going to guess that my antiderivative is this right here. Okay. So here's my guess. F of x, f prime of x. My guess is that the antiderivative is 20 to the x. That's my guess. Let's find the derivative. What is the derivative of 20 to the x? Well, earlier today we said that the derivative of something like this would be 20 to the x times ln of 20 times 1. Right? The 1 comes from the derivative of this guy, right? By the chain rule. The derivative of x, right? The derivative of x is just 1. So this was my guess. This is its derivative. Does this look like what we want it to look like? No. But I mean, it's not too far away. How do I make this to look like that? I have to make all this here disappear. So do I really have to write the times 1? I don't have to. Let me just get rid of it. Really, what I have to get rid of, what I really have to get rid of is this ln of 20. And so what I'll do is I'll multiply by its reciprocal. Both sides, of course. And the purpose behind that is that this will knock this out. And so now it says 20 to the power of x, which is exactly what this says. And so this tells us that this is your antiderivative. And so our original function f would be 1 over ln 20 times 20 to the power of x plus c. Let's check that off. Looks good, right? And let's do maybe one more, and then maybe we can drop another video later on in the week. So what if we do a problem now where we have something with trigonometry? So what if we have this here? What if your derivative says, like, let's say 3, and let's go with sine of 7x. This one's kind of random. It says 3 sine 7x. Okay, so jot that down. And so what would be your guess for the antiderivative? Well, look at your paper because I erased it. Look for your paper, and if your derivative is sine, then what's going to be your guess for the antiderivative? Remember what it said there in the cheat sheet? I think it said something like this here. I think this is what it said, right? If your derivative is something with a sine, then my guess is going to be something with a cosine. So let me make a guess down here in yellow. So I have some function f, and then its derivative, f prime. So my guess is not just cosine. I'm going to go ahead and put cosine of 7x because I see that this has a 7x, okay? This is my educated guess for the antiderivative. Let me take the derivative of my guess. The derivative of cosine is negative sine of the same thingamajig, right? Cosine of blah, blah, blah is negative sine, blah, blah, blah. But then by the chain rule, we have to multiply by the derivative of whatever was in the parentheses. And in the parentheses, it says 7x. And the derivative of that says, or the derivative of that will be 7. So this is my guess. This is its derivative. I have to manipulate this until it looks like that. Well, dude, it's like, how the heck do I make this to look like that? One step at a time. Maybe I can get rid of the negative by just kicking the negative over to this side. And I can do that. Let's say I multiply by a -1. I'll put a -1 right there. Try that again. So the purpose for that is because this -1 knocks this out. Okay. Now, how can I get rid of this 7? Well, I can divide by 7. I can divide by 7. These are gone. So now this says sine 7x, but this has like a mysterious 3 in the front. Well, if you want it to be a 3, then just go ahead and multiply this by 3, but also multiply this one by 3, right? And that way, this looks just like this. There is a 3 sine 7x, and that's exactly what you want. And so over here, if we clean up this mess, I could call this something like this here. I could give the negative to the 3, and I could put that above the 7 to make this -3/7. Plus c. You see that? So the idea, the philosophy that we're employing in this class is make educated guesses. Make an educated guess for the antiderivative. Take the derivative of your guess. Modify that derivative until it looks like what it's supposed to look like. But of course, whatever modifications you make to the derivative of your guess, make those same modifications to your guess. All right, so that's sort of the philosophy that we employed. And this coming week, we'll do something else. And I'll be sure to make a video on whatever we learned this week. So if you have any questions, you can drop them in the comment section below or just email me. So I hope that helped, guys. Have a nice day. See you next time.